Lesson 2 is transformations of exponential functions. So in the upper left corner, we'll start with that formula that has all the different values placed in for all the different types of transformations. And the good news is that they all kind of share the same meaning as they have for every other function that we've studied so far this year. Our base or our parent function is just different. This time it's going to be an exponential. So f of x equals a times b raised to the 1 over b x minus h plus k. The one thing I will point out is that, yes, there's like two different b's. The like uppercase b is going to be like the base of the exponential, and that can vary based on the problem. The lowercase b is going to be the horizontal dilation, kind of like what we studied all year. Okay, so going through each letter, like I said, they have the same meaning. Like the meanings haven't changed. The base is just a little bit different. So a is a vertical dilation. And it can also be a vertical reflection. So if you have a negative a, there would be a reflection there as well. A vertical reflection would be like 1 over the x-axis. So vertical dilation or reflection for a. And then this b is not any sort of transformation. It's just the base of the exponential, and that'll vary based on what the parent function is. And then for this one right here, that lowercase b, that's a horizontal dilation or reflection. So B is a horizontal dilation or reflection. B would be like the stretch or compression like scale factor. But just keep in mind the reciprocal of B does go into the function, so that's why there's a 1 over B here. And then H is our horizontal translation. So that's how far does the graph like shift left or right without actually like changing the shape of the graph. So horizontal translation, that's H. And then that leaves K at the end, and that's going to be the vertical translation. And vertical translation just means like shifting the graph up or down without changing like the like shape or the orientation or anything like that. Okay, and then there is a little note over here, and that's just about like the reflections themselves. We wrote it in with like the vertical and horizontal dilations, but if you see a negative like kind of out in front of the base, that would be a vertical reflection or reflection over the x-axis. If you see a negative like up in the exponent, like with the x, that would be a reflection over the y-axis or a horizontal reflection. Okay, so for like the first half of the notes, we're just going to kind of go over like what kind of causes a transformation in terms of like looking at the function. So I tried to organize by like table and like label each transformation so that you could have like a nice table to refer back to as you're like going through checkpoints and exams. So for all these, we're going to just describe the transformation from f of x to g of x inward. So like translation for left, or like the vertical stretch by 2 or something like that. Okay. So for horizontal translations, the little formula that is just for horizontal translations is this b raised to the x minus h, where h is going to indicate what our horizontal translation is. So like how far are we going left or right? One thing I want to point out before we start with this one is that because there's that minus in front of the h, remember h is kind of like always the opposite of what it looks like it should be. So f of x equals 4 times 5 raised to the x plus 9, and then g of x is 4 times 5 raised to the x minus 2. So the change is happening in the exponent. It's happening with like the number that's being added / subtracted from x. So that is h. That's that number right here. So that's why this indicates a horizontal translation. And then to figure out how far and in what direction, we have to look at how much the value is changing by. So it's going from x plus 9 to x minus 2. So think about if you were like starting at positive 9 and going down to negative 2. Even if you had to count like down like 8, 7, 6, 5, all the way down to negative 2, you would be going down 11. So from here to here, we're going down 11. But remember, h is always kind of like the opposite of what it looks like it should be. So in this case, h would be positive 11. And since it's positive, we're going to go right 11. So I'm going to add translate right 11. Or you could add 11 units, whatever you prefer. So translate right 11. And again, to go from like a x plus 9 down to an x minus 2, you're going down 11. But since h is always kind of like the opposite of whatever it looks like, we got to say h is positive 11, and then that means we're translating right 11. Okay, so for vertical translations, the little mini formula for vertical translations is b to the x plus k. Because the k just has like a plus sign in front of it, we don't have to like switch it or like say it's the opposite of what it looks like. It's much more straightforward than a horizontal translation. So for f of x, it's f of x equals 3 raised to the x minus 2, and g of x is 3 raised to the x minus 2 plus 4. So you can see that there is a number that wasn't here that does get added, like a constant gets added to the end of g of x to get that new function. And that constant added at the end that's our plus k. So that would mean that k is 4. And again, we don't have to switch it. So since there's just like a plus 4 there, k is just regular old 4. Anytime you see a constant tacked onto the end like that or added to something that was already there, that's going to be our k value. Since it's positive 4, we would say translate up 4. And then moving down to horizontal dilation. So there's kind of like a trend, like the horizontal transformations are always like a little bit more difficult than the vertical ones. So with horizontal dilations, you can see the formula is, sorry about the double b's, but b raised to the 1 over bx. And that 1 over b indicates that like whatever the dilation factor is, you're going to have to put the reciprocal of it in the function, or whatever you see in the function, the reciprocal is your factor. So what that means is like f of x is 3 raised to the x plus 10, and then g of x is 3 raised to the 1/2 x plus 10. So you can see that the changes happening like in that exponent with the x, it was an x, and then it's becoming 1/2 x, and the rest of the function is staying exactly the same. So it's happening in the spot that like kind of calls for a horizontal dilation. But because we have a 1/2 inside the function, b is not just 1/2. b is going to be the reciprocal of 1/2, so it's 2. And I would leave a note that like whatever b is going to be the reciprocal of what's inside the function. And vice versa, if you like found the like scale factor from the graph, you would put the reciprocal in the function if you were writing it. So b is 2. And then what that means in terms of like the transformations, I guess I didn't leave myself a ton of space like down below this line, but you can see like right here I have what each value of b means in terms of like a dilation. So if the absolute value of b, or if b is greater than 1, it indicates a horizontal stretch. So since b is 2, and I'm just reading off of this line right here, since b is 2, that would be a horizontal stretch. So that's our transformation. We would say horizontal stretch by a factor of 2. So horizontal stretch by 2. I'm just going to shorten it instead of by factor of 2. So horizontal stretch by 2. And then before we move forward, if you have like a scale factor that's between 0 and 1, so like a half or like 1/3, that would be a horizontal compression. And then moving over to a vertical dilation, same thing here, like the vertical translation is a bit easier than the horizontal one, and the vertical dilation is a bit easier than the horizontal one. So the little formula for vertical dilations is a times b to the x power. So we're really just looking for that number multiplied out in front of the function to change, or to get added if there wasn't one already. So f of x is 5 to the x plus 12, and then g of x is 1/3 times 5 to the x plus 4. So what's happening between like f of x and g of x is that the entire function is getting multiplied by 1/3. And remember, when you like vertically like dilate something, you have to multiply the entire function by that scale factor, which is why this ends up being a 4 over here. So like think if I were to distribute that 1/3 in, it would be 1/3 times 5 to the x power, and then 1/3 times 12. That would change this into a 4. So we're multiplying the original function by a third. That would mean that a is 1/3. And then what that means in terms of like stretch or compression, that's written down here. So when a, or the absolute value of a, is greater than 1, it's a vertical stretch. If it's between 0 and 1 like ours is, it would be a vertical compression. And you may also see like the word vertical shrink instead of compression. That means the same thing. So our transformation, it would be a vertical compression by 1/3. And then notice with like a vertical stretch or compression, I don't have to take the reciprocal of what's in the function itself. It's pretty much straightforward with what it looks like. So whatever number got multiplied in out or out in front, that's our a value. It's more straightforward. We don't have to switch it around. Okay, moving down to a horizontal reflection, which that's a reflection over the y-axis if it switches like side to side. So a horizontal reflection happens by negating the input, and that means that we make the like original x value negative, or the opposite of what it was originally, like opposite sign. So for this one, f of x is equal to 7 to the x power. If I were to want to reflect that horizontally, all I would have to do is take that x and make it into a negative x, and that would reflect it horizontally. So this would be a horizontal reflection, or I'm just going to say reflection over the y-axis. So whenever you see that it was like the x or the input value that got negated, that's a reflection over the y-axis. And just to kind of like go back up to that section, that information was written up here as well. So you can see like it was the x itself that was negative, not the entire like exponential, like the first line. So that's a reflection over the y. And then the last one from this table is the vertical reflection. That's a reflection over the x-axis. So the little formula for that, it's like -1 times b over x. You don't typically write the negative there. However, I didn't want to just put like negative b over x, or I really just wanted to like kind of point out that b itself is not negative. It can't be negative for an exponential. That's a positive value. It would just be the negative that would be like multiplied out in front. So what that means is like if I had, say, negative 2 to the x power, and let's say I were to put in like x equals 4, then it'd be like -2 to the 4th, but that negative doesn't belong to the base, so it would just continue to like stay in front, and you would find like 2 to the 4th, so that would be 16, and the negative would stay out in front. Whereas like if the negative belonged to the base, which it shouldn't for an exponential function, that would actually turn into a positive 16 because you have 4 negatives multiplied together. So just keep that in mind, like with the like vertical reflection or reflection over the x-axis, there will be a negative in front, but it doesn't actually like belong to the base itself. It's just like multiplying the output by a negative to flip it. Okay, so f of x equals 6 to the x power plus 2, and then g of x equals -6 to the x power minus 2. So for this one, you can see like there is now a negative out in front here, and this plus turned to a minus as well. The reason is because it's kind of the same as like a vertical stretch or compression, where if I want to reflect something over the x-axis, I have to multiply the entire like original function by a -1. So then that would become the negative 6x, and then I would have to distribute the negative 1 to the 2 as well, and that's how it turns into a minus 2 instead of a plus 2. So keep in mind for like vertical dilations and reflections, you're multiplying the entire original function by that scale factor, so it would get multiplied by the 6 to the x and by the positive 2 to turn it into a negative 2. And that does happen here, so this would be a reflection over the x-axis. So reflection over the x-axis. Okay, so that first set of notes, if you wanted to refer back to the workbooks, go more with the first two, so like 2.1 and 2.2, and the next set of examples goes along best with 2.3. So example 1, and these examples are pretty much structured the same way, the graphs will just kind of change a bit. So example 1, f of x equals 3 to the x power, we want to write a rule for g of x. So we have to look at the graph and determine what type of transformation is actually happening here. So if we look at like what our original points are, so our points are 2, 9 and 8, 9. So between those 2 points, the y-coordinate is staying the same. It's 9 on both. It's the x-coordinate that's changing. It's going from 2 to 8. So if it's the x-coordinate that is changing, that means that there's some sort of horizontal change that's happening. And then to decide between whether or not it's a horizontal dilation or translation, we have to look at whether or not the shape of the graph is changing. So if the shape is not changing, if it's like maintaining the same structure, that would be a translation where it's just sliding over. If the shape of the graph is changing, like if it's getting more steep or more like flat or narrow, that would be a dilation because the shape is changing. So on this graph, it really does just look like f of x is being slid over to get g of x. The shape or like kind of like this angle of the line is not changing, or like the steepness of the line is not changing. So that would be a translation. So in terms of translations, we have to count how far over the graph is being moved. And since we're going from like the 2 to the 8, that means that it's going 6 to the right. And for horizontal translations, we use that letter h to represent them. So our original function was f of x equals 3 to the x. We want to write a rule for g of x. I'm going to write just more of like a general function rule first before we worry about the 3 to the x part. So it's going to be g of x equals f of x minus h. That's what we would use for a horizontal translation. And then I'm just going to go ahead and take the h out and put the 6 there, since we know h is 6, since we're going 6 to the right. And then now what that means is to write g of x, we have to take the x in f of x and replace it with x minus 6. So like the original function was f of x, where the input was x. If we wanted to write f of x minus 6, we would have to replace the x with x minus 6. So for g of x, it'd be equal to 3, and then instead of just 3 to the x, it would be 3 to the x minus 6, and then that would be our final rule for g of x. So g of x equals 3 raised to the x minus 6. And then moving to example 2, it has the same starting function, f of x equals 3 to the x. We still want to write a rule for g of x, but there's a different change that's happening in the graph. So if we look at this graph, our original 2 points are actually the same as well. So it was 2, 9, and then now it's 8, 9. So it's kind of funky because the numbers are changing the same way. If we look back at example 1, our original point was 2, 9, and then it was changing to 8, 9. So we're still focusing in on those x coordinates, going from 2 to 8 because the 9s are staying the same. So if the x-coordinates are the ones that are changing, it's some sort of horizontal change, and then to decide between horizontal translation and horizontal dilation, we need to see if the shape of the graph is changing, and I think on example 2, it's pretty clear that the shape is changing because f of x is much steeper than g of x, like how that line kind of curves up and to the right, so the shape is changing. So if the shape is changing, that means it's a horizontal dilation. So I'm going to kind of treat it the same way of setting up the function rule rather than just starting with the 3 of x right away. So it'd be g of x equals f of 1 over b to the x. That's the formula that we use for a horizontal dilation. And then to figure out what b is, we have to think about, okay, what scale factor is the function changing by? And scale factor is something that's being multiplied. So I have to ask myself, instead of like, with translations, you're adding. So like we did 2 plus 6 to get to 8. With dilations, you're multiplying. So it's like, what number do you have to multiply 2 by? To get to 8, you would have to multiply by 4. So that would mean that b is 4. So translations, you're looking for like adding or subtracting to slide the function over. Dilations, you would be multiplying. So in this case, b would be 4. So we would take that 4 and put it here. Kind of like inputting into the actual function works the same way, where like here we have f of x and it was 3 to the x power. Our input was x. That's why it ended up here. If we're changing our input to 1 over b or 1 over 4, that's what we have to replace x with. So I'm going to go ahead and take that b out and go ahead and put the 4 in, since we established b was 4, since that was the scale factor we had to multiply the x coordinate by 2 times 4 to get 8. And then now when I write my final function, it'll be g of x equals, I have 3 to the x power, but instead of just 3 to the x, it's going to be this whole thing that goes into my input. So it'd be 3 raised to the 1/4 x. So g of x equals 3 raised to the 1/4 x. Okay, moving down to example 3 and 4. These are the last two. I know they're all kind of similar, but they're like same but different. Okay, so example 3. F of x equals 2 to the x plus 3. We want to write a rule for g of x. So we'll look at the points we're given. They are 1, 5, and then 1, negative 15. So in this case, the x coordinate is staying the same. It's the y coordinate that's changing. It's going from 5 to negative 15. So if you can kind of like see from the graph, it's like the f of x is going like up into the right, and then g of x is going down into the right. So there's also some sort of like reflection that's happening. It looks like it's been flipped upside down. So what's kind of cool is if you have a vertical dilation and a vertical reflection, you actually get to kind of take care of it all in one step, which is nice. We just have to figure out what is the scale factor that's getting us from that like y coordinate of 5 to negative 15. So to get from 5 to negative 15, I have to multiply by negative 3. So I can just say a equals negative 3, and then that's going to be enough to help me set up my function. So I'll treat this the same way. I'll write the function notation first. So it'll be g of x equals, and then when we have a vertical stretch and or a vertical reflection, that looks like a times f of x. So the only thing that's changing, well, not the only thing, depending on what your original function is, but what's happening is you're multiplying a, like, kind of like a coefficient, like a number out in front, by that original function. We just figured out that that number we have to multiply in is 3 to get the stretch from 5 to 15, and the reflection to get from not only a positive 5, but down to a negative 15. So I'm going to take out that a and just replace it with negative 3. And then now to write my function, I just need to go ahead and put all of f of x into this f of x. I don't have to worry about changing the x at all. It's not changing the input. I'm just multiplying the original function by negative 3. So it'll be negative 3. And then I'm going to use parentheses for f of x to make sure I multiply everything by that negative 3. So it'd be 2 to the x power plus 3. And then you do want to like simplify and distribute in, so that would be the last step. So it'd be g of x equals negative 3 times 2 to the x power. You don't actually get to multiply the 3 and the 2. You have to write it as negative 3, and then either a parentheses or a dot to the x power. And then don't forget to multiply the negative 3 by the positive 3 at the end. So negative 3 times 3, that should be negative 9 out here. So the reason that we can't like multiply the 3 and the 2 together, it kind of even goes back to like order of operations where like PEMDAS, you would simplify exponents before multiplication. And since the exponent is a variable, we can't simplify it. Like, we can't just skip it. You would have to simplify exponent first before multiplication. Since we don't know the exponent, we pretty much have to stop there and we can't multiply them together. So the final answer would be g of x equals negative 3 times 2 to the x power minus 9. And then this is the last example, example 4. I highly recommend trying to pause the video and work through it on your own and just kind of checking your work along the way. So example 4, f of x equals 2 raised to the x minus 1, and we want to write a rule for g of x. So f of x, our original point is 2, 3, and then on g of x, our original point is 2, 9. So you can see again, the change is happening in the y coordinate. So in the y coordinate, it's going from 3 to negative 9. And you can also see that the shape of the graph is changing, so there's some sort of dilation, and it's also getting flipped upside down, so there's some sort of reflection as well. So if we are having a vertical dilation, meaning the y coordinate is getting multiplied by a scale factor, and the graph is flipping upside down, meaning it's reflecting vertically or reflecting over the x-axis, we get to kind of do that all in one step. So it's very similar to example 3. So we just have to figure out what is the number that we have to multiply 3 by to get to negative 9. So I have to multiply 3 by negative 3 to get to negative 9. And then since this is a vertical dilation and a vertical reflection, that's all going to be the A value. So A is a vertical dilation and reflection. B is going to be a horizontal dilation and reflection. That's all up at the top of the page as well. So I can say A equals negative 3. And then I'm going to write just the general function formula for this. So g of x is going to be equal to, since it's a vertical dilation, A times f of x. And we just figured out that A needs to be negative 3 to make this happen. So I'm going to take out the A and put the negative 3 there. And then now, since it's just negative 3 times f of x, I can just take my original f of x and put it in there for negative 3. So it'd be g of x equals negative 3. I'm going to put f of x in parentheses so I don't forget to multiply that second part by it. So it'd be 2 to the x power minus 1. And then I need to go ahead and distribute that negative 3 in to get my final answer. So it'd be g of x equals negative 3 times 2 to the x, and then same thing, we're not multiplying those numbers together. It'll just stay out in front. We'll just leave a dot or parentheses to show that they're being multiplied, times 2 to the x, and then negative 3 times negative 1 would turn into a positive 3. So altogether, g of x equals negative 3 times 2 to the x power plus 3. Okay, so for these notes, I highly recommend having this table kind of stored so you can refer back to along with the formula up at the top.